Cool. So this time I'm going to talk about word representation and text classifiers. These are kind of the foundations that you need to know in order to move on to the more complex things that we'll be talking in future classes. But actually, in particular, the word representation part is pretty important. It's a major thing that we need to do for all NLP models. So let's go into it. So last class, I talked about the bag of words model. And just for review, this was a model where basically we take each word, we represent it as a one-hot vector like this. And we add all of these vectors together. We multiply the resulting frequency vector by some weights, and we get a score out of this. And we can use the score for binary classification, or if we want to do multi-class classification, we get multiple scores for each class. And the features F were just based on our word identities, and the weights were learned. And if we look at what's missing in bag of words models, we talked about handling of conjugated or compound words. We talked about handling of word similarity. And we talked about handling of combination features and handling of sentence structure. And so all of these are tricky problems. We saw that creating a rule-based system to solve these problems is non-trivial and at the very least would take a lot of time. And so now I want to talk about some solutions to the problems in this class. So the solution to the first problem, or a solution to the first problem, is subword or character-based models. And that's what I'll talk about first. Handling of word similarity, this can be handled using word embeddings. And the word embeddings will be another thing we'll talk about this time. Handling of combination features, we can handle through neural networks, which we'll also talk about this time. And then handling of sentence structure. The kind of standard way of handling this now is through sequence-based models, and that will be starting in a few classes. So let's jump into it. So subword models. As I mentioned, this is a really, really important part of all of the models that we're building nowadays, including state-of-the-art language models and things like this. And the basic idea behind this is that we want to split, in particular, split less common words up into multiple subword tokens. So to give an example of this, if we have something like the companies are expanding, it might split companies into companies and expanding like this. And there are a few benefits of this. The first benefit is that this allows you to parameters between word varieties or compound words. And the other one is to reduce parameter size and save compute and memory. And both of these are kind of like equally important things that we need to be considering. So does anyone know how many words there are in English? Any ideas? Yeah. 2 million. Pretty good. Any other ideas? Yeah. Some models use 60,000. I think 60,000 is probably these subword models when you're talking about this. So they can use subword models to take the 2 million, which I think is a reasonable guess, to 60,000. Any other ideas? 700,000. Okay, pretty good. So this was a fair question. It doesn't really have a good answer, but 200 million is probably pretty good. 700,000 is pretty good. The reason why this is a trick question is because our company and companies different words. Maybe not, right? Because if we know the word company, we can guess what the word companies means. What about automobile? Is that a different word? Well, maybe if we know auto and mobile, we can kind of guess what automobile means, but not really. So maybe that's a different word. There's all kinds of shades of gray there. And also, we have really frequent words that everybody can probably acknowledge are words like the and maybe car. And then we have words down here, which are like misspellings or something like that, misspellings of actual correct words or slang or other things like that. And then it's questionable whether those are actual words or not. So there's a famous law called Zipf's law, which probably a lot of people have heard of. It's also the source of your .zip file, which is using Zipf's law to compress outputs by making the more frequent words have shorter byte strings and less frequent words have less frequent byte strings. But basically, like, we're going to have an infinite number of words or at least strings that are separated by white space. So we need to handle this somehow, and that's what subword units do. So 60,000 was a good guess for the number of subword units you might use in a model. And so by using subword units, we can limit to about that much. So there's a couple of common ways to create these subword units. And basically, all of them rely on the fact that you want more common strings to become subword units. Or actually, sorry, I realize maybe before doing that, I could explain an alternative to creating subword units. So the alternative to creating subword units is to treat every character or maybe every byte in a string as a single thing that you encode and predict. So in other words, instead of trying to model the companies are expanding, we model T, H, E, space, C, O, M, et cetera, et cetera. Can anyone think of any downsides of this? Yeah. Yeah, the set of these will be very small, but that's not necessarily a problem, right? Yeah. Any other ideas? Yeah. Yeah, the resulting sequences will be very long. And when you say difficult to use, it could be difficult to use for a couple of reasons. There's mainly two reasons, actually. Any ideas about those? Yeah, yeah. Yeah, that's a little bit of a separate problem than the character-based model. So let me get back to that. But let's finish the discussion of the character-based models. So if it's really long, maybe a simple thing like let's say you have a big neural network and it's processing a really long sequence. Any ideas what happens? Basically, you run out of memory, or it takes a really long time, right? So you have computational problems. Another reason why is think of what a bag of words model would look like if it was a bag of characters model. It wouldn't be very informative about whether like a sentence is positive sentiment or negative sentiment, right? Because instead of having G-O-O-D, you would have, instead of having good, you would have G-O-O-D, and that doesn't really directly tell you whether it's positive sentiment or not. So those are basically the two problems, compute and lack of expressiveness in the underlying representation. So you need to handle both of those. Yes.
So if we move from character to word for better expressiveness, can we assume that if we just get bigger and bigger sentences, paragraphs, we'll get even better expressions?
Yeah, so very good question. I'll repeat it. And actually, this also goes back to the other question you asked about words that look the same but are pronounced differently or have different meanings. And so, like, let's say we just remembered this whole sentence, right? The companies are expanding. And that was like a single embedding, and we somehow embedded it. The problem would be we're never going to see that sentence again. Or if we go to longer sentences, we're never going to see the longer sentences again. So it becomes too sparse. So there's kind of a sweet spot between like long enough to be expressive and short enough to occur many times so that you learn appropriately. And that's kind of what subword models are aiming for. And if you get longer subwords, then you'll get things that are more expressive but more sparse. In shorter subwords, you'll get things that are like less expressive but less sparse. So you need to balance between them. And then once we get into sequence modeling, they start being able to model like which words are next to each other, which tokens are next to each other and stuff like that. So even if they are less expressive, the combination between them can be expressive enough. So yeah, that's kind of a preview of what we're going to be doing next. Okay, so let's assume that we want to have some subwords that are longer than characters but shorter than tokens. How do we make these in a consistent way? There's two major ways of doing this. The first one is byte pair encoding, and this is very, very simple. In fact, it's so simple that we can implement it in this notebook here, which you can click through to on the slides. And it's about 10 lines of code. And so basically what byte pair encoding does is that you start out with all of the vocabulary that you want to process, where each vocabulary item is split into the characters and an end of word symbol. And you have a corresponding frequency of this. You then get statistics about the most common pairs of tokens that occur next to each other. And so here, the most common pairs of tokens that occur next to each other are ES, because it occurs 9 times, because it occurs in newest and wildest. Also ST and TW, because those occur there too. And then you have WE and other things like that. So out of all of the most frequent ones, you just merge them together. And that gives you new EST and wide EST. And then you do the same thing. This time now you get EST. So now you get this suffix EST. And that looks pretty reasonable for English, right? You know, EST is a common suffix that we use. It seems like it should be a single token. And so you just do this over and over again. If you want a vocabulary of 60,000, for example, you would do 60,000 minus number of characters merge operations. And eventually you would get a vocabulary of 60,000. And yeah, very, very simple method to do this. Any questions about that? No? Yeah. Mm-hmm. Mm-hmm.
Having a sweet spot on, as you mentioned, the length, the thing of the physical. So I'm curious about the research that focusing on the information created side of it and the design.
Yeah, so just to repeat the comment, this seems like a greedy version of Huffman encoding, which is similar to what you're using in your zip file, a way to shorten things by getting longer, more frequent things being encoded as a single token. I think byte pair encoding did originally start like that. That's part of the reason why the encoding thing is here. I think it originally started there. I haven't read really deeply into this, but I can talk more about how the next one corresponds to information theory. And Tuesday, I'm going to talk even more about how language models correspond to information theories. So we can discuss maybe in more detail then too. So the alternative option is to use unigram models. And unigram models are the simplest type of language model. I'm going to talk more in detail about them next time, but basically the way it works is you create a model that generates all words in the sequence independently. Sorry, I thought I had an equation, but basically the equation looks like this. So you say the probability of the sequence is the product of the probabilities of each of the words in the sequence. And then you try to pick a vocabulary that maximizes the probability of the corpus given a fixed vocabulary size. So you try to say, okay, you get a vocabulary size of 60,000. How do you pick the best 60,000 vocabulary to maximize the probability of the corpus? And that will result in something very similar. It will also try to give longer vocabulary, more common vocabulary, longer sequences, because that allows you to maximize this objective. The optimization for this is performed using something called the EM algorithm, where basically you predict the probability of each token showing up, and then select the most common tokens, and then trim off the ones that are less common, and then just do this over and over again until you drop down to the 60,000 vocabulary limit. So the details for this are not important for most people in this class because you're going to just be using a toolkit that implements this for you. But if you're interested in this, I'm happy to talk to you about it. Yeah.
Is there a problem with assuming the independence?
Oh, in unigram models, there's a huge problem with assuming independence in language models, because then you could rearrange the order of words in sentences. That's something we're going to talk about in language modeling next time. But the good thing about this is the EM algorithm requires dynamic programming in this case, and you can't easily do dynamic programming if you don't make that assumptions. And then finally, after you've picked your vocabulary and you've assigned a probability to each word in the vocabulary, you then find a segmentation of the input that maximizes the unigram probabilities. So this is basically the idea of what's going on here. I'm not going to go into a lot of detail about this because most people are just going to be users of this algorithm, so it's not super, super important. The one important thing about this is that there's a library called sentence piece that's used very widely in order to build these subword units. And basically what you do is you run the sentence piece train program, and that gives you, you select your vocab size. This character coverage is basically how well do you need to cover all of the characters in your vocabulary or in your input text. What model type do you use? And then you run this sentence piece encode file to encode the output and split the output. And there's also Python bindings available for this. And the one thing that you should know is by default, it uses the unigram model, but it also supports BPE. In my experience, it doesn't make a huge difference about which one you use. The bigger thing is how big is your vocabulary size. And if your vocabulary size is smaller, then things will be more efficient, but less expressive. If your vocabulary size is bigger, things will be more expressive, but less efficient. And a good rule of thumb is like something like 60,000 to 80,000 is pretty reasonable if you're only doing English. If you're spreading out to things that do other languages, which I'll talk about in a second, then you need a much bigger vocabulary size. So there's two important considerations when using these models. The first is multilinguality, as I said. So when you're using subword models, they're hard to use multilingually because, as I said before, they give longer strings to more frequent strings, basically. So then imagine what happens if 50% of your corpus is English, another 30% of your corpus is other languages written in Latin script, 10% is Chinese, 5% is Cyrillic script languages, 3% is Japanese, and then you have like 0.01% written in like Burmese or something like that. Suddenly, Burmese just gets chunked up really, really tiny, really long sequences, and it doesn't work as well. So one way that people fix this And actually, there's a really nice blog post about this called Exploring BERT's Vocabulary, which I referenced here if you're interested in learning more about that. But one way that people work around this is if your actual data distribution looks like this, like English, Chinese, actually, sorry, I forgot the Indian languages in my example. Apologies for that. Hindi, all the other ones are there. So like, let's say we have Hindi. What you do is you essentially create a different distribution that like downweights English a little bit and upweights all of the other languages, so that you get more of the other languages when creating the vocabulary. So this is a common workaround that people do for this. The second problem with these is arbitrariness. So as you saw in my example with BPE, ES, ST, and T end of word symbol all have the same probability or have the same frequency, right? So if we get to that point, do we segment ES or do we EST or do we segment EST? And so this is also a problem, and it actually can affect your results, especially if you like don't have a really strong vocabulary for the language you're working in or you're working in a new domain. And so there's a few workarounds for this. One workaround for this is called subword regularization. And the way it works is instead of just having a single segmentation and getting the kind of maximally probable segmentation or the greedy one that you get out of BPE, instead you sample different segmentations at training time and use the different segmentations, and that makes your model more robust to this kind of variation. And that's also actually the reason why Sentence Piece was released was through this subword regularization paper. So that's also implemented in Sentence Piece if that's something you're interested in trying. Cool. Are there any questions or discussions about this? Yeah. Yeah.
If we want to have another novel language, can we come to an equation because so if we really already think about tons of text already. So if we adding that the novel language would be very educational and efficient. So if there ways to like work around the ways to do it.
Yeah, so this is a good question. Just to repeat the question, it was like, let's say we have a big multilingual subword model, and we want to add a new language in some way. How can we reuse the existing model but add a new language? It's a good question. If you're only using it for subword segmentation, one nice thing about the unigram model here is this is kind of a probabilistic model. So it's very easy to do the kind of standard things that we do with probabilistic models, which is like, let's say we had an old vocabulary for this. We could just interpolate we could interpolate like this and just, combine the probabilities of the two and then use that combined probability in order to segment the new language. Things like this have been done before, but I don't remember the exact references for them. So, but that's what I would do here. Another interesting thing is, this might be getting a little ahead of myself, but there's a there's a paper that talks about how you can take things that were trained with another vocabulary. And basically the idea is you pre-train on whatever languages you have, and then you learn embeddings in the new language. You freeze the body of the model and learn embeddings in the new language. So that's another method that's used. It's called on the cross-lingual transferability of bilingual representations. And I'll probably talk about that in the last class of this thing, so you can remember that then. Cool. Any other questions? Yeah. Is bag of words a first step to process your data if you want to do generation? Do you mean like a word-based model or a subword-based model, or?
Yeah, like saying you have generation. Like if there's where in the pipeline is this first step?
So the subword segmentation is the first step of creating just about any model nowadays. Like every model uses this, and they usually use this either to segment characters or bytes. Characters are like Unicode code points, so they actually correspond to an actual visual character, and then bytes are, many Unicode characters are like 3 bytes. Like a Chinese character is 3 bytes, if I remember correctly. So the byte-based segmentation is nice because you don't even need to worry about Unicode. You can just do you can just segment the file like literally as is. And so a lot of people do it that way too. Llama, as far as I know, is bytes. I believe GPT is also bytes. But previous to like 3 or 4 years ago, people used characters also. Cool. Okay, so this is really, really important. It's not like super complex, and practically you will just maybe train or maybe just use a tokenizer, but that's an important thing to know. Cool. Next, I'd like to move on to continuous word embeddings. So the basic idea is that previously we represented words with a sparse vector with a single one, also known as one hot vector. So it looked a little bit like this. And instead, what continuous word embeddings do is they look up a dense vector. And so you get a dense representation where the entire vector has continuous values in it. And I talked about a bag of words model, but we could also create a continuous bag of words model. And the way this works is you look up the values of each vector, the embeddings of each vector. This gives you an embedding vector for the entire sequence. And then you multiply this by a weight matrix, where so this is columns. So the rows of the weight matrix correspond to the size of this continuous embedding, and the columns of the weight matrix would correspond to the overall number of labels that you would have here, and then that would give you scores. And so this basically what this is saying is each vector now, instead of having a single thing that represents which vocabulary item you're looking at, you would kind of hope that you would get vectors where words that are similar by some concept of similar, like syntax, semantics, whether they're in the same language or not, are close in the vector space. And each vector element is a feature. So for example, each vector element corresponds to, is this an animate object, or is this a positive word, or other other things like that. So just to give an example here, this is totally made up. I just made it in Keynote, so it's not an actual vector space. But to illustrate the concept I showed here, what if we had a 2-dimensional vector space, where the 2-dimensional vector space, the x-axis here is corresponding to whether it's animate or not, and the y-axis here is corresponding to whether it's like positive sentiment or not. And so this is kind of like our ideal goal here. So why would we want to do that? Yeah, sorry, go.
On the slide about the functions,
Mhm.
like what do the, like in the one hot interval, it's 1, 0, 0.
Yep.
What is the, like the four entries be here?
So what would the four entries be here? The four entries here are learned. So they are, they're learned just together with the model. And I'm going to talk about exactly how we run them soon. But the final goal is that after learning has happened, they have these two properties, like similar words are close together in the vector space. And that's like number one, that's the most important. And then number two is ideally these features would have some meaning, maybe human interpretable meaning, maybe not human interpretable meaning, but yeah. So one thing that I should mention is I showed a contrast between the bag of words, the one hot representations here, and the dense representations here, and I used this lookup operation for both of them. And this lookup operation actually can be viewed as grabbing a single vector from a big matrix of word embeddings. And so the way it can work is like we have this big vector, and then we look up word number 2 in a zero index matrix, and it would just grab this out of that matrix. And that's practically what most like deep learning libraries or whatever library you use are going to be doing. But another way you can view it is you can view it as multiplying by a one hot vector. And so you have this vector, exactly the same matrix, but you just multiply by a vector 0, 0, 1, 0, 0, 0, 0, 0, and that gives you exactly the same thing. So the practical implementations of this tend to be the first one, because the first one's a lot faster to implement. You don't need to multiply like this big thing by a huge vector. But there are advantages of knowing the second one. Just to give an example, what if you, for whatever reason, you came up with like a crazy model that predicts a probability distribution over words instead of just words? Maybe it's a language model that has an idea of what the next word is going to look like. And maybe your model thinks the next word has a 50% probability of being cat, 30% probability of being dog, and 2% probability, 20% probability of being bird. You can take this vector and multiply it by the matrix and get like a word embedding that's kind of a mix of all of those word embeddings, which might be interesting and let you do creative things. So knowing that these two things are the same is kind of useful for that kind of thing. Any questions about this? I'm going to talk about how we train next, so maybe I could go into that. Okay, cool. So how do we get the vectors? Like the question asked before. So up until now, we trained a bag of words model. And the way we trained a bag of words model was using the structured perceptron algorithm, where if the model got the answer wrong, we would either increment or decrement the embeddings based on whether the label was positive or negative, right? So I showed an example of this very simple algorithm. You don't even need to write any like NumPy or anything like that to implement that algorithm. Here it is. So we have like 4x, y in data. We extract the features, we run the classifier, we have the predicted y, and then we increment or decrement the features. But how do we train more complex models? So I think most people here have taken a machine learning class of some kind, so this will be reviewed for a lot of people. But basically, we do this by doing gradient descent. And in order to do so, we write down a loss function, calculate the derivatives of the loss function with respect to the parameters, and move the parameters in the direction that reduces the loss function. And so specifically for this bag of words or continuous bag of words model, we want this loss function to be a loss function that gets lower as the model gets better. And I'm going to give two examples from binary classification. Both of these are used in NLP models reasonably frequently. There's a bunch of other loss functions, but these are kind of the two major ones. So the first one, which is actually less frequent, is the hinge loss. And then the second one is taking a sigmoid and then doing negative log likelihood. So the hinge loss, basically what we do is we take the max of the label times the score that is output by the model and 0. And what this looks like is we have a hinge loss where if y is equal to 1, the loss if y is greater than 0 is 0. So as long as we get, basically, as long as we get the answer right, there's no loss. As the answer gets more wrong, the loss gets worse, like this. And then similarly, if the label is negative, if we get a negative score, then we get 0 loss and the loss increases if we have a positive score. So the sigmoid plus negative log likelihood, the way this works is you multiply y times the score here. And then we have the sigmoid function, which is just kind of a nice function that looks like this, with 0 and 1 centered around 0. And then we take the negative log of this sigmoid function, or the negative log likelihood. And that gives us a loss that looks a little bit like this. So basically, you can see that these look very similar, right? The difference being that the hinge loss is sharp, and we get exactly a 0 loss if we get the answer right. And the sigmoid is smooth, and we never get a 0 loss. So does anyone have an idea of the benefits and disadvantages of these? I kind of flashed one on the screen already, but. So I flashed that on the screen, so I'll give this one and then I can have a quiz about the sigmoid. But the hinge loss is more closely linked to accuracy. And the reason why it's more closely linked to accuracy is because basically we will get a 0 loss if the model gets the answer right. So when the model gets all of the answers right, we will just stop updating our model whatsoever because we don't have any loss whatsoever. And the gradient of the loss is 0. What about the sigmoid and negative log likelihood? There's kind of two major advantages of this. Anyone want to review their machine learning class? Sorry, what was that? For ROC, yeah, maybe there's a more direct. I think I know what you're saying, but maybe there's a more direct way to say that. Yeah. Yeah, so the gradient is non-zero everywhere, and the gradient also kind of increases as your score gets worse. So that's one advantage. It makes it easier to optimize models. Another one, linked to the ROC score, but maybe we could say it more directly. Any ideas? Okay, basically the sigmoid can be interpreted as a probability. So if the sigmoid is between 0 and 1, and because it's between 0 and 1, we can say the sigmoid is a probability, and that can be useful for various things, like if we want a downstream model or if we want a confidence prediction out of the model. So those are two advantages of using a sigmoid plus negative log likelihood. There's no probabilistic interpretation to something trained using the hinge loss, basically. Cool. So the next thing that we do is we calculate derivatives. And we calculate the derivative of the parameter given the loss function. To give an example of the bag of words model and the hinge loss, the hinge loss, as I said, is the max of the score times y. In the bag of words model, the score was the frequency of that vocabulary item in the input multiplied by the weight here. And so this is a simple enough function that I can just do the derivative by hand. And if I do the derivative by hand, what comes out is if y times this value is greater than 0. So in other words, if this max picks this instead of this, then the derivative is y times freq. and otherwise it is in the opposite direction. Then optimizing gradients, we do standard in standard stochastic gradient descent, which is the most standard optimization algorithm for these models. We basically have a gradient over, we take the gradient over the parameter of the loss function, and we call it GT. So here, sorry, I switched my terminology between W and theta. So this could be W, the previous value of W. And this is the gradient of the loss. And then we take the previous value, and then we subtract out the learning rate times the gradient. And there are many, many other optimization options. I'll cover the more frequent one called ATOM at the end of this lecture, but this is the basic way of optimizing the model. So then my question now is, what is this algorithm? With respect to, this is an algorithm that is that has a loss function. It's calculating derivatives, and it's optimizing gradients using stochastic gradient descent. So does anyone have a guess about what the loss function is here, and maybe what is the learning rate of stochastic gradient descent? I kind of gave you a hint about the loss function, actually. And just to recap what this is doing here, it's if predicted y is equal to y, then it is moving the feature weights in the direction of y times the frequency vector. Yeah. Yeah, exactly. So the loss function is hinge loss, and the learning rate is 1. And just to show how that corresponds, we have this if statement here, and we have the increment of the features. And this is what the derivative looked like. So we have if this is moving in the right direction for the label, then we increment, otherwise we do nothing. So basically, you can see that even this really simple algorithm that I implemented with a few lines of Python is essentially equivalent to this stochastic gradient descent that we do in models. So the good news about this is, this is really simple, but it only really works for like a bag of words model or a simple feature-based model. But it opens up a lot of new possibilities for how we can optimize models. And in particular, I mentioned that there was a problem with combination features last class, like don't hate and don't love are not just, hate plus don't and love plus don't. It's actually the combination of the two is really important. And so, yeah, just to give an example, we have don't love is maybe bad. Nothing I don't love is very good. And so in order to solve this problem, we turn to neural networks. And the way we do this is we have a lookup of dense embeddings. Sorry, I just realized my coloring is off. I was using red to indicate dense embeddings, so this should be maybe red instead of blue. But we take these dense embeddings, and then we create some complicated function to extract combination features, and then use those to calculate scores. And so we calculate these combination features. And what we want to do is we want to extract vectors from the input where each vector has features. Oh, sorry, this is in the wrong order. So I'll get back to this. So this was talking about the continuous bag of words features. So the problem with the continuous bag of words features was we were extracting features like this. but then we were directly using the dense features that we extracted to make predictions without actually allowing for any interactions between the features. And so neural networks, the way we fix this is we first extract these features. We take these features of each word embedding, and then we run them through kind of linear transforms in nonlinear, like linear multiplications and then nonlinear transforms to extract additional features. And finally, run this through several layers and then use the resulting features to make our predictions. And when we do this, this allows us to do more interesting things. So like, for example, we could learn a feature combination. A node in the second layer might be feature 1 and feature 5 are active. So that could be like feature 1 corresponds to negative sentiment words like hate, despise, and other things like that. So for hate and despise, feature 1 would have a high value like 8.0 and then 7.2. And then we also have negation words like don't or not or something like that. And those would have don't and not. Would have a high value for like feature 5 or something. And so these would be the word embeddings where each word embedding corresponded to, features of the words. And then after that, we would extract feature combinations in this second layer that say, oh, we see at least one word where the first feature is active, and we see at least one word where the fifth feature is active. So now that allows us to capture the fact that we saw like don't hate or don't despise or not hate or not despise or something like that. So this is the way this is a deep continuous bag of words model. This actually was proposed in 2015. I don't think I have the reference on the slide, but I think it's in the notes on the website. And actually, at that point in time, there were several interesting results that showed that even this like really simple model did really well at text classification and other simple tasks like that, because it was able to, share features of the words and then extract combinations of the features. So in order to learn these, we need to start turning to neural networks. And the reason why we need to start turning to neural networks is because while I can calculate the loss function of the loss function of the hinged loss for a bag of words model by hand, I definitely don't. I probably could, but don't want to do it for a model that starts to become as complicated as this with multiple matrix multiplications and TANHs and stuff like that. So the way we do this, just a very brief coverage of this because I think probably a lot of people have dealt with neural networks before. The original motivation was that we had neurons in the brain where each of the neuron synapses took in an electrical signal, and once they got enough electrical signal, they would fire. But now the current conception of neural networks or deep learning models is basically computation graphs. And the way a computation graph works, and I'm especially going to talk about the way it works in natural language processing, which might be a contrast to the way it works in computer vision, is we have an expression that looks like this, and maybe it's the expression x corresponding to a scalar. And each node corresponds to something like a tensor, a matrix, a vector, a scalar. So scalar is kind of 0-dimensional. It's a single value, 1-dimensional, 2-dimensional, or arbitrary dimensional. And then we also have nodes that correspond to the result of function applications. So if we have x be a vector, we take the vector transpose. And so each edge represents a function argument and also a data dependency. And a node with an incoming edge is a function of that edge's tail node. And importantly, each node knows how to compute its value and the value of its derivative with respect to each argument times the derivative of an arbitrary input. And functions can be basically arbitrary functions. It can be unary, nullary, unary, binary, n-ary, often unary or binary. And computation graphs are directed and cyclic. And one important thing to note is that you can have multiple ways of expressing the same function. So this is actually really important as you start implementing things. And the reason why is the left graph and the right graph both express the same thing. The left graph expresses x transpose times a times x, whereas this one has x, a, and then it puts it into a node that is x transpose ax. And so these express exactly the same thing, but the graph on the left is larger. And the reason why this is important is for practical implementation of neural networks. The larger graphs are going to take more memory and going to be slower usually. And so often in a neural network toolkit like PyTorch, which we're going to look at in a second, you will have something, you will be able to do this, or you'll be able to do like this. So these are two different options. This one is using more operations, and this one is using less operations. And this is going to be faster because basically the implementation within PyTorch will have been optimized for you. It will only require one graph node instead of multiple graph nodes. And that's even more important when you start talking about like attention or something like that, which we're going to be covering very soon. Attention is a very multi-head attention or something like that is a very complicated operation. So you want to make sure that you're using the operators that are available to you to make this more efficient. And then finally, we could like add all of these together at the end. We could add a constant. And then we get this expression here, which gives us kind of a polynomial expression. Also, another thing to note is within a neural network computation graph, variable names are just labelings of nodes. And so if you're using a computation graph like this, you might only be declaring one variable here, but actually there's a whole bunch of stuff going on behind the scenes, and all of that will take memory and computation time and stuff like that. So it's important to be aware of that if you want to make your implementations more efficient and other things. So we have several algorithms that go into implementing neural nets. The first one is graph construction. The second one is forward propagation. And graph construction is basically constructing the graph, declaring all the variables, stuff like this. The second one is forward propagation. And the way you do this is in topological order. You compute the value of a node given its inputs. And so basically you start out with all of the nodes that you give as input. And then you find any node in the graph where all of its tail nodes or all of its children have been calculated. So in this case, that would be these two nodes. And then in arbitrary order, or even in parallel, you calculate the value of all of the satisfied nodes until you get to the end. And then the remaining algorithms are back propagation and parameter update. I already talked about parameter update using stochastic gradient descent. But for back propagation, we then process examples in reverse topological order, calculate derivatives of parameters with respect to the final value. And so we start out with the very final value. Usually this is your loss function. And then you just step backwards in topological order to calculate the derivatives of all of these. So this is pretty simple. I think a lot of people may have seen this already, but keeping this in mind as you're implementing NLP models, especially models that are really memory intensive or things like that, is pretty important. Because if you accidentally, like for example, calculate the same thing twice, or accidentally create a graph that is manipulating very large tensors and creating very large intermediate states, that can kill your memory and cause big problems. So it's an important thing to be aware of. Cool. Any questions about this? Okay, if not, I will go on to the next one. So neural network frameworks, there's several neural network frameworks, but in NLP nowadays, I really only see two and mostly only see one. So that one that almost everybody uses is PyTorch. And I would recommend using it unless you, if you're a fan of like Rust or, esoteric, not esoteric, but like unusual programming languages and you like beauty and things like this. Another option might be JAX. So I'll explain a little bit about the difference between them and you can pick accordingly. First, both of these frameworks are developed by big companies and they have a lot of engineering support behind them. That's kind of an important thing to think about when you're deciding which framework to use because, it'll be well supported. PyTorch is definitely most widely used in NLP, especially NLP research, and it's used in some NLP projects. JAX is used in some NLP projects. PyTorch favors dynamic execution. So what dynamic execution means is you basically create a computation graph and then execute it every time you process an input. In contrast, there's also, you define the computation graph first and then execute it over and over again. So in other words, the graph construction step only happens once, kind of at the beginning of computation, and then you compile it afterwards. And it's actually PyTorch supports kind of defining and compiling, and JAX supports more dynamic things, but the way they were designed is kind of favoring dynamic execution or favoring definition and compilation. And the difference between these two is this one gives you more flexibility. This one gives you better optimization and more speed if you want to do that. Another thing about JAX is it's kind of very close to NumPy in a way. Like it uses a very something that's kind of close to NumPy. It's very heavily based on tensors. And so because of this, you can kind of easily do some interesting things like, okay, I want to take this tensor and I want to split it over 2 GPUs. And this is good if you're training like a very large model and you want to put kind of this part of the model, you want to put this part of the model on GPU 1, this on GPU 2, this on GPU 3, this on GPU 4. It's slightly simpler conceptually to do in JAX, but it's also possible to do in PyTorch. And PyTorch by far has the most vibrant ecosystem. So like, as I said, PyTorch is a good default choice, but you can consider using JAX if you like new things. Cool. Yeah, actually, I already talked about that. So in the interest of time, I may not go into these very deeply, but it's important to note that we have examples of all of the models that I talked about in the class today. These are created for simplicity, not for speed or efficiency of implementation. So these are kind of PyTorch-based examples where you can create the bag of words model, a continuous bag of words model, and a deep continuous bag of words model. And all of these, I believe, are implemented in model.py. And the most important thing is where you define the forward pass. And maybe I can just give a simple example of this, but here, this is where you do the word embedding. This is where you sum up all of the embeddings and add a bias. And then this is where you return the score. And then, oh, sorry. The continuous bag of words model sums up some embeddings, or gets the embeddings, sums up some embeddings, gets the score here and then runs it through a linear, or changes the view, runs it through a linear layer. And then the deep continuous bag of words model also adds a few layers of like linear transformations and damage. So you should be able to see that these correspond pretty closely to the things that I had on the slides. So hopefully that's a good start if you're not very familiar with implementing models in PyTorch. Oh, and yes, the recitation will be about playing around with sentence piece and playing around with these. So if you have any, look at them, have any questions, you're welcome to show up for a walkthrough. Cool. Any questions about these? No? Okay. So a few more final important concepts. Another concept that you should definitely be aware of is the atom optimizer. So there's lots of optimizers that you could be using, but almost all research in NLP uses some variety of the atom optimizer. And the way this works is it optimizes the model considering the rolling average of the gradient and momentum. And the way it works is here we have a gradient, here we have momentum, and what you can see is happening here is we add a little bit of the gradient in. How much you add in is with respect to the size of this beta 1 parameter, and you add it into the momentum term. So this momentum term like gradually increases and decreases. So in contrast to standard gradient descent, which could be updating each parameter kind of like very differently on each time step, this will make the momentum kind of transition more smoothly by taking the rolling average of the gradient. And then the second thing is by taking the momentum. This is the rolling average of the, I guess, gradient variance. Sorry, this should be variance. And the reason why you need to keep track of the variance is some parameters will have very large variance in their gradients and might fluctuate very strongly, and others might have smaller variance in their gradients and not fluctuate very much. But we want to make sure that we update the ones, we still update the ones that have a very small change in their variance. And the reason why is kind of, let's say you have a multi-layer network. Or actually, sorry, a better example is like, let's say you have a big word embedding matrix, and over here we have like really frequent words, and then over here we have gradient. No, you have like less frequent words. We want to make sure that all of these get updated appropriately. All of these get like enough updates. And so over here, this one will have lots of updates. And so kind of the amount that we update, or the amount that we update this will be relatively large. Whereas over here, this will not have very many updates. We'll have lots of 0 updates also. And so the amount that we update this will be relatively small. And so this kind of squared gradient here will be smaller for the values over here. And what that allows us to do is it allows us to, maybe I can just go to the bottom. We end up dividing by the square root of this. And because we divide by the square root of this, if this is really large, like 50 and 70, and then this over here is like 1, 0.5, 0.3 or something, we will be upweighting the ones that have like less square gradients. So it allows you to upweight the less common gradients more frequently. And then there's also some terms for correcting bias early in training, because these momentum and variance, or momentum and squared gradient terms, are not going to be like well calibrated yet. So it prevents them from going very haywire at the beginning of training. So this is the details of this, again, are not like super important. Another thing that I didn't write on the slides is now in transformers, it's also super common to have an overall learning rate schedule. So even Adam has this ADA learning rate parameter here. And what we often do is we adjust this. So we start it low, we raise it up, and then we have a decay at the end. And exactly how much you do this kind of depends on how big your model is, how much data you're training on eventually. And the reason why we do this is transformers are unfortunately super sensitive to having a high learning rate right at the very beginning. So if you update them with a high learning rate right at the very beginning, they go haywire and you get a really weird model. But you want to raise it eventually so your model is learning appropriately. And then in all stochastic gradient descent, no matter whether you're using Atom or anything else, it's a good idea to gradually decrease the learning rate at the end to prevent the model from continuing to fluctuate and getting it to a stable point that gives you good accuracy over a large part of data. So this is often included. Like if you look at any standard transformer training recipe, it will have that included in it as well. So that's kind of the go-to optimizer. Are there any questions or discussion? There's also tricky things like cyclic learning rates where you decrease the learning rate, increase it, and stuff like that, that I won't go into that and don't actually use it that much. Second thing is visualization of embeddings. So normally when we have word embeddings, usually they're kind of large, and they can be like 512 or 1024 dimensions. And so one thing that we can do is we can downweight them, reduce the dimensions or perform dimensionality reduction and put them in like 2 or 3 dimensions, which are easy for humans to visualize. This is an example using principal component analysis, which is a linear dimension reduction technique. And this is an example from 10 years ago now, one of the first major word embedding papers where they demonstrated that if you do this sort of linear dimension reduction, you get actually some interesting things where you can draw a vector that's almost the same direction between like countries and their capitals, for example. So this is a good thing to do, but actually PCA doesn't give you, in some cases, PCA doesn't give you super great visualizations. Sorry. Yeah.
Work well for like, if it's like 768, like about 768, right? The number of dimensions. Does that really work for it?
For things like this, I think you probably would still see vectors in the same direction, but I don't think there's a reason why I'm introducing nonlinear projections next, because the more standard way to do this is nonlinear projections, in particular, a method called t-SNE. And the way they do this is they try to group things that are close together in high dimensional space so that they're also close together in low dimensional space. But they remove the restriction that this is linear. So this is an example of just grouping together some digits from the MNIST data set, reducing the dimension of digits from the MNIST data set according to PCA. And you can see it gives you these kind of blobs that overlap with each other and stuff like this. But if you do it with t-SNE, this is completely unsupervised, actually. It's not training any model for labeling. The labels are just used to draw the colors. And you can see that it gets pretty coherent clusters that correspond to like what the actual digits are. However, one problem with t-SNE, I still think it's better than PCA for a large number of applications, but settings of t-SNE matter. And t-SNE has a few settings. Kind of the most important ones are the overall perplexity hyperparameter and the number of steps that you perform. And there's a nice example of a paper or kind of like online post that demonstrates how if you change these parameters, you can get very different things. So if this is the original data, you run t-SNE and it gives you very different things based on the hyperparameters that you change. And here's another example. You have 2 linear things like this. And so PCA, no matter how you ran PCA, you would still get a linear output from this. So normally, it might change the order, it might squash it a little bit or something like this. But if you run Tisney, it gives you crazy things. It even gives you like DNA and other stuff like that. So you do need to be a little bit careful of that. This is not necessarily going to tell you nice linear correlations like this. So like, let's say this correlation existed. If you use Tisney, it might not necessarily come out to use Tisney. So cool. Yep. That's my final thing. Actually, I said sequence models in the next class, but it's in the class after this. I'm going to be talking about language modeling. So, cool. Any questions or?